Hello everybody, how's it going? Welcome to another stream. Yeah, so today we're gonna actually, okay, I've already seeded in that directory, it's good. So today we're gonna get started on the Sphere Raytracer tile binning. Hey there Egotist, how you doing? Last stream we was hoping to get started on that, but we basically came across a big problem, which basically meant we didn't really end up doing much on that stream. So I basically binned that stream and we'll basically restart it with this one. So the problem that we bumped into last stream, which we're going to throw away, is effectively, so here's the Sphere ray tracing code, and I've just put a little debugging thing in here where we just effectively draw a box around each sphere. And this is the problem we've been trying to solve, right? Can we get a box in screen space around a sphere? So we've just done the most simple way of doing it right now. And that is just translate a 3D bounding box into screen space. Hey, they're not so red. Not doing bad, man. Not doing bad. How you doing? Hey there, Kate Moy. Kate Moy. I keep forgetting how to forget to pronounce your name. Hey. Doing alright. Implemented basic C test framework today. Cool. So that's fun. Nice. Yeah, days not going bad. Just kind of was supposed to get an extra hour's sleep today, but then I didn't because I just woke up early, like even earlier. So there's that. But yeah, it's not going bad. Yesterday I just sort of exercised, and it was my mum's birthday on Friday, so I just went for a meal with the family. So it was good to see the family. But yeah, it's been pretty good. Just chilling. You know, just also trying to tackle this screen bounds for a sphere problem as well. I've been trying to tackle this thing. Right, I got an Iron Brew. So we got a different drink this week, Iron Brew. Oh yeah. So the reason why we need a screen access line bounding box is because we want to bin these spheres per tile. Because currently, the problem is per pixel, every pixel is testing against every single sphere on the screen. And we want to minimize. We want each pixel to have like a list of probable spheres that it will intersect with. And that will increase the performance massively. So we needed a way to get a bounding box around a sphere, basically. I've tried some other methods, so I guess I can just go to my Twitter feed. Yes, this is the method we're probably just going to go with for now. Effectively, we just put a bounding box around the sphere in 3D, right? We take the two important corners, depending on which place it is on the screen. This also goes for the y-axis as well. Essentially there's four corners, and then you can basically just project that back into the near plane, and then you got your bounding box. But it isn't the best bounding box, right? It doesn't fit nice and snug around it. So for big spheres, it's kind of like wasted space. But for small spheres, it's not as bad, but it's still probably going to go into some tiles it shouldn't go in, and increase the list size. But it's like really cheap to do this bounding box. So it might be the best way to do it, I don't know. Yeah, I've tried to do some other methods, but it's actually quite a difficult problem to get a perfect box around a sphere in screen space. It can't be done with simple trigonometry. It has to be done. Yeah, there's probably like two. Yeah, it's a bit of a hard problem. Let's just leave it at that. So I'll probably try and tackle that problem off stream and see if I can explain exactly how it's been solved. But until then, so we're just gonna make a function called get. Yeah, ABB should hopefully be enough. Like, it's not that much wasted space, and I imagine, like, that's how complicated it is, right? But then as you try and solve it better, it gets more and more complicated code. You know, this is one that someone did, RCN, I think it is, RCT in the chat. Did this, I ported it over and it didn't quite work on different field of views. But yeah, it's quite a good solution, but it is 40% slower because it's got a bunch of square roots in it. And it's also a lot more maths operations happening. So I'm not sure if the complexity is going to actually help us. Hey there, AB, how's it going? Right, so calc, sphere, screen bounds. That's what we'll call it. So we're just going to have this function we can call, and that way in the debug, we can debug visualize it in the sphere ray tracer, but then also use it in the sphere tiler, right? The tile binning code. Was all that? Okay, that's not it. Perry boy, how's it going? Good to see you, pal. How you been? Perry, you missed the unveiling of the primitive we'll be using for graphics. It's right up your alley. Good mate, all you? How's my number? Yeah, doing good, doing good. Bit tired, but I'm holding on in there. Yeah, it's very tiring. I can say. But yeah, we're doing good though. He's really cute and amazing, but tiring boy. He took his jabs like a champ, you know. He just sort of pulled the fat lip like, but you know, it's good. How's things going with you? Computer only graphics, love it. Yeah, man. It's the same thing too. Sweet. Yeah, we've been effed by Vulkan. Completely effed. So, yeah. Right, we'll get the other ones working in a bit. I think we want to... Yeah, okay. So this one will return... Oh, it's too much... Right. Here we go. If 0... Perfect. Then we'll say, hey... Right, so we get the min-max... Why don't we transition the min-max all the way up? Where's the near clip plane distance? Let's transition it all the way up and get rid of the rest. All the way up to screen space. Get rid of all that and just return. Return as a float. Oh, screw it. Let's do that. F30 times 4 min screen space x. We'll say splat 2. Hopefully this works. So I just say xy, make a float 4. I'm good, thanks. Pretty much feeling like passing out soon. Just drove 4 hours journey to see my granddad. Wow, it's a long way. Does he live up north then or something? Sounds like an up north journey. Hey there, welcome. If I didn't make it your name, it's Blue. Ah, go, Matt. Arcia. Welcome. The north to me, but Midlands, so not that north. Excellent. It's up north. That's all we need to know, us down south people. Past London, up north. Gomitaka. Gomitika. I probably butchered that like mad, but there you go. Welcome. How's it going? Right, so we've made that function now, so we can use it for the debugging code. If 0 right, and if we should probably put a nice little thing here to say, oh, if you want to visualize the AABBs, yeah, so we'll call this like bounds. It's bounds in screen space. So what was that? Count sphere screen bounds, perfect. We need to pass in a bunch of parameters in here. We need to pass in the sphere, S, and f32 pixel, yeah. Pixel size and near clip plane, so we can transition that to screen space. Right. You finally gone Wayland? Nah. Nah, that's not it. Basically, Perry, the basic primitive that we're rendering with is balls. And I knew you'd love it. So everything's been rendered with 100% spheres. Bear in mind, these are spheres. The lighting's just been... Yeah, let me just sort this one out. Wait a second. I'll show you them proper colored in. They kind of just forced being white right now, but you know. So yeah, we're just gonna be putting a bunch of balls everywhere, and it's gonna be good. It's gonna be good. It can have its own distinct look, you know. Does Mrs. know you're up playing with ball? Yeah. Yeah, she knows. I show her every time I finish. I'm like, here's the balls I've made. Look how good these balls are. They have lighting now. Yeah. But yes, this is my life. So where are we going to next? Yeah, so just trying to... Oh, Ray Origin. Ooh. So we'll just call it like camera origin. Camera. Right, let's get that compiling. Wait, I knew that splat wouldn't work. Yeah, something doing my preprocessor. It's... Man, preprocessors in C. Like, it does the recursive macro stuff fine. Well, not well, okay. Yeah, it does complicated macro stuff fine, but this one there's a slight bug in this one place. When it unfolds that, or expands that, it just doesn't quite work. Oh well. Sweet, compiles again. Right. Yeah, so we've got some basic lighting. It isn't the best, right? We just pretend there's a light coming in from the top. So, all my days, we're bugging it up now. What have I done? It's all disabled code. Not sure exactly. Could it just be the test scene? Oh, okay, there's no color coming in. That's why. Yeah. So what we didn't... I've got a new test scene just to sort of... It hasn't got colors set, basically. So just ignore putting colors down. So we could just say S equal red. That'll do it. There you go. Yeah, it's just got some basic lighting, nothing fancy. So just pretending there's a light that's sort of like just sort of coming from behind the camera downwards. So just in a simple like dot product and checking if they're pointing in the opposite directions. So that's what we've got for now. But what we're trying to do is, so this is rendering 9 spheres, I think. Yeah. So it's taking about 0.17 ms to render 9 spheres because per pixel we're doing a ray versus sphere check. So if you obviously add 100 spheres, what you're saying is every pixel is going to test 100 spheres. So we're going to break these spheres into tiles. So let's go to the UI render code and just visualize what the tiles will look like. So there'll be like a little array per tile. Oh, I need to actually render some UI. That's in main, isn't it? Here we go. So basically, where these overlap with a tile, well, not quite. We'll get the bounds back up, but effectively, we'll sort of, place these spheres in the arrays for each of these tiles that they kind of overlap with. We can't get it perfect. See, the other thing we could have done. So we're taking the bound. Okay, let's imagine this actually. So let's re-enable this debug code. Where we've got this calculate sphere bounds. We need to pass in the sphere, the ray origin, and the pixel size at near clip plane. That gets you your bounds. Bounds.x. Wait. Yeah, bounds xy. Oh, no. Something like this. Half dims, bounds, ZW, bounds, XY. That's the half dimensions. And then you sort of work out position, which is add bounds XY half dims. So that should be able to debug visualize the box. Right, we can't really see it because they're only like 1 pixel wide. Let's get rid of the UI. The boxes are in the wrong place again. Probably because we didn't transition it into... take a look. Right. We need to also get the width and height of the we need to get the screen dimensions, right? So effectively you need to offset by half of the screen dimensions. Kind of missed that. Okay, let's roll with, what is this? Oh yeah, BC output dims. I think the type is wrong. Yeah. U32. There we go. Oh shoot. They're only in the top right hand corner because we did a little trick where we sort of absoluted the result to get rid of the negative numbers. And right, here's a good way to explain it. So effectively we need different corners when we're taking these back into screen space. But if you absolute it, they're the same corners, right? It's basically mirrored. So if we absolute it, we get this corner only. And so we're dealing with the min-max within this corner, so we can just take these guys and project those into screen space. But yeah, I'm just going to undo what we did. Alright, so undo that. We'll just copy and paste the... Started making the change to it here, so it's the problem. I didn't quite copy the bit I wanted. That's it. So I think I just had another idea as well on how we could do this. So this just gets a very simple axis line bounding box. Another way we could do it in the tiler, or when we do the tile binning, is project the tile into the scene and see if it collides with the sphere. I might think about that for a second, but we might not do that today purely because it'll take time. But I might just think about it. Yeah, then this wants it's really silly. This could definitely be written better, but we'll just do a simple version for now. It's probably not a big deal. So min is in the first XY, max is in the next XY. Solve the problem better later. Hey there, Tice, how you doing? Welcome back. How you been? Alright, Y coordinate. Alright. Sweet. So we got our bounds back, right? So where these bounds overlap Again, they're a little bit off, but where these overlap those tiles that we saw, those are the bins they're going to go in. So what we've got to do is, like with the UI, where we do that tile binning, we've got to go ahead and make one of these for the spheres, but it's going to be different. Instead, we're going to iterate, well, each thread is going to get its own sphere, and it will iterate over all of the tiles it can go in, and basically atomic right them in. So I don't think we're going to have massive spheres. All the spheres are probably going to be around the same sort of size, so we won't have to worry about different threads having different lifetimes and wasting sort of wave. I think it's called wave occupancy or something like that. I think we should be fine. Doing good. I see you're still hard at work. Yes, man. Definitely so. Got some made some good progress, actually. Got some 2D graphics now. Got some hook up controllers, keyboard, mouse, all that stuff. So now we're just in the 3D graphics R&D, because I'm hoping to, you know, be able to render lots of spheres where we can sort of use that as the basic building block, and hopefully it looks nice. Right, we're going to see if we get some good lighting on it, and sort of explore this area effectively. Yeah. So now we calculate the screen bounds. We're just going to write that shader now. So let's copy a compute shader and go full ham. So sphere tile binning. So here's our push constants. What do you need for the tile binning? Well, you just need a bunch of spheres. That's what you need, a bunch of spheres. So we get the array of spheres, and that's what we'll be working with. And then we need to have... So here's the other tiling. Yes, we need to have the tile spheres. We need a right only Wallaby. And would you be copying the whole sphere? Yeah, you might copy the whole sphere in. I'm not sure. Because if you just copy indices, when the shader reads over, it'll be very sparse. Yeah, I think we'll copy the whole sphere in. So this whole sphere right now is this, right? So it's like 5 floats. So we might have a limit of like 8 floats. So we'll basically be copying 8 floats around versus copying 1 integer, right? And the logic might be that you'll essentially be creating a linear array, a nice linear array of memory that it can just read from, as opposed to getting a bunch of indices that has to go and fetch sparsely, right? That's the hope. We'll see how that goes. So these are the tile spheres, and we'll pre-allocate this array to the maximum number of tiles. But my one like concern is you don't have how many. You don't have an integer in here that you can use, because I've now made it 8 floats. Like a waste a sphere basically, or in a separate array, I'll store a bunch of atomic integers. But it might not be efficient, all the atomic integers sitting next to each other in memory. I'm not sure if that's a good idea. Hmm. So maybe we waste a sphere and just reuse. Nah. You're not sure what's a good idea about it, to be honest. Well, we're gonna have to have a play with it, I think. Um, we should be able to toggle between both, basically. Oh, I hate when it picks up both of them. Yeah, so we might use the color as the atomic integer place, I think. Yeah, we'll use that. Yeah. All right, so let's just start with this one. See where we get to. So how it's going to work is each thread, right, that gets executed on here is going to be 132. Good. So there's 32 threads per compute unit. This is like the standard, basically. So it's 32 threads that run in lockstep. Each thread is going to get its own sphere. So you need to get your sphere index. So your sphere index will be dispatch index x, right? Because we're not using y and z, we're just doing x. So when we dispatch the compute shader outside, we'll say, oh, we've got sphere count divided by 32 rounded up, and we'll launch that many. So we say if the sphere, because it can be rounded up to 32, if this thread is greater than or equal to spheres count, that was lowercase, spheres count, then we are just going to return and not do anything. Sweet. So now the whole job of this sphere, or this thread, is to get the bounds of the sphere. See, I'm not sure how good of an idea this is, actually. It might be fine. It's very short-lived. We'll see how it is. We'll play around different versions. Let's get the bounds out. So your sphere would be BC spheres, sphere index, camera origin. This is something we need to pass in to. So it'll be like camera. Technically, we probably want something more complex. We had this in the, to define some matrix transform for the camera, right? So anyway, camera position, screen dimensions, we need that to be passed in as well. And then we need this sort of pixel size at near clip plane. So we need like a field of view to be passed in. Yeah, I don't know if we really want to calculate this every time. But yeah, we could definitely pre-calculate that on the CPU and pass it in. Right. Yeah, there's things to be done better, but it's good to get a good base metric first, and can always optimize it. Yeah, so we don't have to keep doing this sort of calculation all the time. Maybe that could get compiled out, because it's all constants, isn't it? So maybe that can just get compiled out. So we've got the bounds now. Now I'm just going to do a lovely for loop over the bounds, right? So you've got your min-max xy bounds. So you go over your y's first, right? So your y equals 0, or y equals bounds y, right? We start there, and then we say y is less than bounds w, right? Because z is actually x, end x, w is end y. and then we say y plus equal the size of a tile, right? This is in screen space. So we kind of need to start, well no, so the tile information, tile dims, yeah, we need the size of a tile. Should be done programmatically. Yeah, so we need that passed in as well. Plus equal constants tile dims dot x. Well, it's y, isn't it? Sweet. So advance by one whole tile. So let's think about this for a second. So you'll start off advance by. So if you advance by a whole tile, but you go into that tile still, it doesn't make. We should probably advance by the difference between. You should round y up to the nearest multiple of tile dims. Yeah, so you probably do something like y equals round up. See, I've got this function, but I keep forgetting where it is. Third party HCC lib hmaths. What we're doing, didn't scale, isn't it? Yeah. Round, okay, so we'll squish like that. Right, round up to multiple. This guy. Beautiful thing. We might not have to use this, right? But it just solves the problem for now. I'll do y plus 1, right? Super hacky. Round up to nearest multiple of that, please. Right. Could probably be done better. There we go. So skip like 8 pixels and yeah. Cool. So now the next thing is you obviously want to do the same thing for the x-axis. So you're going over all those. That'll be z, x, x, x. So z meaning obviously the end x coordinate. So this will go over all the screen bounds. And now all we have to do is effectively atomically add to an integer which represents the number of spheres inside this tile, and then we basically get an index back. So you get an insert index, and this would just be atomic add. Now, thinking about it, I probably can't just use the tile yeah, we might just do a separate array. It's just so nice having it. Yeah, so the problem we're sort of dealing with now is, so here's our buffers, right? We've got the spheres that we'll be reading from, and each thread will get its own sphere. We've then got these tile spheres, which is basically like a bunch of small arrays next to each other. And, you know, each tile has 64 spheres. So we need a place to store the atomic integer. Bear in mind the atomic integer needs to be set to 0. It probably needs to be set to 0 at the beginning of the frame or something. Yeah, what do we do for the... Oh no, we didn't have this problem. It's designed slightly differently. We'll just do this. Read write buffer tile sphere spheres counts. Hey there, I can't even pronounce your name at all. Welcome. How you doing? How's things going? Okay, so we've got this new place we can add these things in. So we've got to fold out. Oh shoot, I've just realized. Tile dims isn't what we're talking about, it's tile size. We still need tile dims. Tile dims is like how many tiles fit on the screen. Tile size is how big is a tile. So this is tile size. Hey Nav. Welcome, hey Nav. How you doing? Welcome to the stream, sir. So we need to then make a flat index. Right, so it'll be a better way might just be convert these into tile bounds, right, into tile space rather than screen space, and then iterate over the tiles. And then this would just be a lot more effective, I think. Yeah. So what you want to do is round down to nearest multiple, round up to nearest multiple, and then divide it by the tile size. And then that should be good. So you'll say like bounds.x equals round down to multiple of bounds. Right, so just repeat that. Y, Z, W, W, Z, Y. So the top two are down, the other two are up. Run down to multiple, run up to multiple. Sweet. So these are now. Oh yeah, then you want to do the division, isn't it? So you just divide it by. See, if you just divided it, and then you could just floor it, right? Then you won't need this complicated function. So you just say this divided by, and then you can just say like, so these will do floor, these will do seal, and voila. So now these are the bounds in convert bounds from screen space to tile space. Now it's going over the tiles. So you could probably just work with them as integers now. And then plus equal 1, plus equal 1. And then just to flatten it out, it's just BC tile dims dot x, right, times by the width plus the x. So let's just flattening that out. And now we can finally get the spheres count, which is tile index. And we're adding 1. Here's our insert index. So this is where we're going to insert our sphere. Now with this insert index, there's like a maximum size. And we haven't really got any constants in yet, but we should really start putting constants in because this is, yeah, we just need to start. So we'll probably have like 64. If it's less than 64, we're going to go ahead and insert our sphere into the tile array. So you need like a base index, tile spheres, base index, and effectively it's tile index times by how many spheres you have per tile. So that's 64 at the moment. And that's your base index. And you can just say base index plus the insert index. And we're just going to copy a whole sphere into there, like so. Where's the sphere? Oh, it's here in it. See, I don't know how much of a good idea this is. Copying whole spheres around. If they're 8 bytes or something. We'll have a play around with it. We'll test an indexed version as well and see how much better it is. Hey, I'm Kept Payne. How's it going? You're not missed much. We're just gone over the. Yeah, it's not too much, my friend. We've literally just started around this tile binning thing. We haven't done. Yeah, that's literally this code here is all that we've done. I've moved I've moved all this code I did off stream to sort of do the bounds of the AABB. Sorry, the bounds of the sphere in screen space. I've moved that into a separate function. That's all we've done. So yeah, so for those who don't know, effectively I've been a bit stuck on how to solve this problem well. So I've just gone with the sort of simplest solution, and that is I want to know how big a sphere is in screen space, so we can bin the spheres into an array of spheres per tile, right? So we have a nice small list of spheres per tile, so when we sort of ray trace against the spheres, we can just be like, right, what pixel are we ray tracing against? Here's a nice small list that you can test against. So we just need effectively a box around the spheres. Now, as you can tell, this box isn't that good of a box, but it's not the whole screen. And for small spheres, it's not that bad, which is a good thing, because we probably just want to have a bunch of small spheres anyway. So I'm going to try and solve this problem off stream better, but it's a bit difficult. But yeah, so effectively we just sort of like, so we know that the screen is mirrored. Effectively, the field of view, the way it kind of affects the corners the most. So you can sort of assume that it's. So we sort of take any coordinate, we absolute the coordinate, and we. What's the best way to describe it? We need to find the two most important edges of the 3D axis line bounding box that get distorted the most. So it's kind of like this top right one and this lower left one. This is the minimum, this is the maximum. So we just basically pick the one that's furthest away at the back on the left, lower left, and one that's the furthest closest to us at the top right. And this is your min, this is your max. And we leverage the fact that the screen could be broken into 4 pieces that we just, absolute the coordinate and just work it out there, basically. So yeah, we just take these corners and map them back onto the near plane, and then map that into screen space, and that gets us our boundary. But again, we do get some wastage. So that's all I've done off stream, is just make a function that sort of calculates this box. Something like this. I'm hoping to do it better someday, but for now it's good enough. So that's all this function does here. And then we just going over all of those. So the tiles are probably like 8 by 8 in size. Have we got a render for that? Yeah. So we render this. Yeah. So here's our spheres with the little boxes around them, right? When they're small, ain't that bad. We render some UI quick with the tile visualizer on. Here we go. This is what we're going to be putting these spheres into, is these tiles. They're like 8 by 8 inside, and that each one of these will hold a list. So whenever we render a pixel in the tile, we get the list for that tile, and we just go over the spheres for that tile. Obviously, a sphere can go into multiple tiles, right? That's all we're doing. Yeah, that's it. Yeah, posted on Discord and on Twitter. I've been trying to get people's help on this because it's quite a difficult problem. I could probably go and explain it, but it's a bit much. There's Effectively, because you're dealing with field of view and it changes, like, you're not dealing with right angles anymore. It's a bit of a hard problem. But yeah. And this is very simple to calculate with a little bit of wastage for the data that we're using, I think. But we'll see. Hey Gavril, how's it going? No clip, welcome. Would it be worth it to translate the spheres into projected space? Spheres to projected space. Yeah, so you can't project the sphere. If you project the sphere, yeah, but you can't project, like, what you're seeing on the screen is the distortion. So if you project the sphere into 2D space, what you're dealing with is not a sphere anymore. It's an ellipse in most cases. There's also another technical term, I think it's called a hyper something. I forgot it exactly, but you're dealing with a different shape. So you actually, yeah, it's not a sphere anymore, right? When it's mapped into 2D space. The other solution I've just thought about doing is, why don't you project the tile into 3D space and do it, but then it's 2D, a flat 2D thing. So if you can somehow project a tile out into 3D space, you're dealing with a, is a plane? Is it a plane? No, it's a weird skewed thing, isn't it? But you could probably round the. You could probably. Hello, next Raytracing. What are you trying to do? Oh no. So what we were doing is we've tried to calculate the bounds of a sphere in screen space, because I want to bin these per tile. And I was just describing how it's been a bit of a pain the past few days trying to work that out effectively. Oh no, we can't take the tile and take it to sphere space or into world space, because we want to know the bounds. We want to know the bounds right away, so we can only test the tiles that we need to. Right. So we ask what the bounds of the sphere are. It gives us back a little box, like a rough box around it. And we start at the bottom left, actually, of it. And then we just march to the right. And then we go up one, march to the right. And we only touch the tiles that we need to and put them in those tiles. Is it worth the effort? Spheres are a nice case. Cones, on the other hand. Hey there, RCT, how's it going? Thanks for your help earlier on the in Discord. What do you mean by cones, though? What does a cone have to do with this? Can it make it easier? I'm not sure what you mean by cones. Alright, so this to say with the UI debugging stuff. For lighting, usually you see lots of people worrying about binning their cone-shaped lights. Right. Right, yeah, they're binning them so they can, yeah, reduce the number of lights to the object they're lighting. Right. Yeah, people do like little special shapes as well, don't they? Yeah. see. Let's put the sphere in there. That's all we're trying to achieve, isn't it? And the counts are in there. Right. So what we're going to do is we're going to do a nice little tidy up of this. I need to and just double check it, and then we'll allocate the arrays, set it all up, give it a run. I want to, I've got to start putting constants into place. So here we go. GFX, sphere. What were we doing? Number of times. Well, okay. Is this something that we do? Maybe we can have it passed in. We can always have it passed in, right? Tile spheres. Count. Cap. Capacity. There we go. Rightio. So I don't know if there's much that we really want to clean up on this. It is compiling. So we've just got these, hard-coded field of view and all that lot. We get the screen bounds or rough screen bounds of our sphere. We turn it into tile space. We go over all the tiles. We atomic add the counts. We need to clear this to 0. We need to find a good place for that. I have got a way to clear memory in the GPU abstraction, so we could just use that. I don't know what we did for the UI. I think in the frame initialize shader, we just did stuff like that. Very small amount of work, so it's just setting parameters. So just set the dispatch args, and that's something simple. Right, I think that's fine. So we'll probably just run that zeroing thing. Okay, let's start dispatching this. So before we do the ray tracing, we want to do some of this. I also want to make sure that we zero some memory. So GPU command buffer 0. Now the buffer that we want to refer to is a new one, which we haven't done yet, and this is going to be called sphere tile spheres counts. Yeah, okay. Buffer ID, long name. Right. So we want to zero that whole buffer. So it's just going to do that for us. So we can just atomic add 1 to it. Now we need to go ahead and assign all of this information. Finally finished HTC, that's right, Elspill. How's it going? It's been a while. Finished it about 6 months ago now. How you been? So we've been running a game about an engine. We're about 51 episodes in now. Got like game controller support. We've got obviously keyboard mouse game controller. Got custom UI, immediate mode UI that we've written. Got GPU abstraction. We're just in 3D graphics R&D right now. When I did binning and ray tracing, I just cut the screen up into parts as there are cores and then shoot the rays through them. You can get fancy worker threads and stuff, so the cores Don't idle. Right, you're talking about CPU side. Yeah, so the thing is about the GPUs, you get tons and tons of threads and stuff, so yeah. Good, good. Schoolwork got me really busy, but finally got on into some Wayland programming again. Nice. Currently trying to glue my Wayland window creation library into my Flutter embedder. Cool. I was looking into BVH building for ray tracing. I was going to do this myself as some radix sort and BVH construction in CUDA was fun. Cool. Yeah, I don't know. I want to avoid BVH because the problem is I'm dealing with a ton of data. Well, that's the idea. I'm hoping, right, that we can just put tons of spheres down. And the thing that I'm hoping is we can do some like fancy animations, and I don't want to tie a sphere. Like we're gonna have like models, right, and animation, but I don't want to tie a sphere to a model when we render it because I want it to be loose, and I don't want to have any. I want to try and avoid having like occlusion culling, um, where you assume a model is solid, right? There's no holes in it, because we might have some fancy animation where you sort of do something and gaps appear, and I want it to be fully. I want to be working with a base with the base unit of a sphere for everything when we try to do rendering. So we'll see how many spheres we can actually do. But we might have, but when we do like probably shadowing and lighting, we might make some, we might build some form of um, I'm not sure what we'll do there though. Um, yeah, actually no, we might have to follow the same rule. I'm not sure. But yeah, I think we want to just work with the base unit of a sphere and not worry about like I don't want to optimize it by grouping the spheres together because that's when you start having problems. But maybe I might group them in every frame to something like around some sort of area, local area, but nothing that persists between frames, I think is a good way of saying it. GPU resource ID, one of them. Which ones do we need? We need just a bunch of spheres. We've already got that one in it. Tile spheres. So RCT, you're saying you're doing the ray tracing in CUDA. Do they expose like a ray tracing API? Or are you sort of just doing like software ray tracing in CUDA? I've heard good things about CUDA. Right, let's jam. Let's jam. Ooh. Right, so I'm gonna take these guys and put them here next to the other one, spheres buffer ID. Okay, so how many tiles? Oh my days. This is jam. Right, so we need to have something where right. Sphere tile size min 8, something like that. And obviously because this is just a bunch of demo code, we're just, ain't gonna be super clean until we know exactly what we want. Right, so this just works out basically how many tiles we have on the whole screen, right? So x times y divided by x times y. Well, sorry, x times y pixels divided by x times y pixels per tile. That gives us how many sphere tiles we're gonna have. So we need to know how many. Oh, bugger. Hey, Jamega, how's it going? Welcome. How you been? Oh, I don't think CUDA has any built-in ray tracing support. My GPU so doesn't support it. Because the basic texture stuff, that's about it. Oh, okay. Yeah, it's pretty insane they support C++, basically C++ in there. It's cool though. Then people can just work in work in a language that everyone's used to working in. Unlike GLSL. Yeah, you share code. Yeah. Well, yeah, that's true. I think what I mean is like it's good that they at least support C++, the language. So like, but yeah, I see what you're saying though. Like SC, like standard library, not the best. Get your stud unique putter all in that GPU. So how do we decide how many? You know what, screw it, let's make it a hard-coded number. Well, let's do 64 of them for now. So what was it again? The spheres, this one. Sweet. Jobs guden. So we just want the tiles capacity. So this one's times by E32, right? It's just a bunch of counts. And this one is multiplied by tile spheres capacity, so times by 64 times by size of spheres. And voila, there we go. Easy peasy. So we're going to make sure we do synchronization code as well when we fit all these boys in. So here's the spheres buffer. We need access to that. We then need the tile spheres output buffer, tile spheres counts. The number of spheres we've got loaded into the system, into this one here, the spheres buffer. Output dimensions, we like output dimensions. Let's chuck them in. Hard coded as crap, but oh well. Tile dimensions. How did we fill that in last time? Right, let's go change the UI one. Don't know why I didn't prefix this earlier. Right. Okay. Their code is template hell. They use them for tile size and other constants. Funny to see the function name when it's buried in 5 lines of templates. Oh boy. Yeah. Yup. See, I kind of forget about that world because I, just stick in C. It's a bit like when people who don't know much about what it's like to make a website, like, just think it's like so much better than it actually is. I just forget how bad that stuff is. Um, so where's the? Yeah, I think we'll just put it next to here as well. We'll just do another one. We'll just do like sphere tile size. So we can just change this number here. We'll just do 8. Maybe we'll do 16. I know we were seeing 16 on the debug thing earlier, so maybe it's alright. We're not doing chunks. We don't need chunks. XKCD, is it? No, okay. Oh no, what have you done? Let's make it small, just in case. Is this safe? Okay. Why? It's just text, okay. I'm sure we can all handle a bit of text. Yeah, we definitely need an adult filter on this. This is. I wouldn't show my child this. I want to protect their eyes. Right. Yeah, my eyes don't know where to sort of just snap to sort of just get the gist of this. Um, yeah, this is the kind of problem with template stuff. Exactly, that's what we're talking about. Program C is better than anything we've got over there. That's right, just in time. But yeah. Conditional T. Right up my alley. Yeah, it just reads like English. I cannot see what your problem is. Oh yeah, let's not do that. Yeah, this is not what the stream's about. Yeah, don't worry. On YouTube, I'll explicitly make sure it's not that. Change it. Hmm. Right. So just to make sure we're right here. Uh, Wait a minute. Tile size. I think you need a cell size as well. Yeah, so what is tile size? What is a cell size? A cell is what we process in the shader, I think. Um, yeah, so a cell is like our is what we'll be using for our local dispatch arguments. But your tile could actually be bigger than that, meaning that your local workgroup size is. Wait a minute. Yeah, I forgot the exact specifics. Yeah, so effectively, when we go down to here, see where's the UI renderer? Yeah, it's using cell size. Perfect. So here we'll be using cell size. That's 8 by 8. Oh. Right. Nearly there. And then we can blow up the computer. I know we all like that. Okay, so now I've got this number here. And this one here, we can pass those into the shaders. So tile dims, sphere, tile dims, and sphere tile size. So you might think we're nearly done. Well, we've got to do a dispatch and synchronization. So we could automate synchronization by just reading the structure. I've got some reflection information, but I've not hooked that up, so we've got to be manual about it. So we're reading from spheres, we're writing out to tile spheres, and we're reading and writing onto tile spheres counts, which is the atomic buffer. So then we're going to launch the shader, which is tile binning. And this is going to be the number of spheres that we have divided by spheres count. Oh, why did I set that to itself? Spheres count divided by 32, rounded up to nearest 32. And this is going to be dispatch of 1 on the Y, 1 on the X. And this is size of tile binning. Right. So I think we're there. Obviously, we haven't hooked up the ray tracer to be using the tiles yet. But yeah. Let's just run it and see if it makes the machine blow up. Right, so the good old question is, we like to do these polls because, you know, will the GPU crash? Do you guys have faith in me? Will the shader we've just written crash the GPU and therefore shut down the stream for a minute? Will it happen? That's the question. Hey Sully, so I sent my friend some Stone Rebel music and he and told him the vocalist is a huge fan of G. Guevara. Listened to it for 20 minutes before getting pissed because I told him, yep. That was a good one. Although I don't know who G Guevara is, Sully, but that was a good joke. I still got it. Right. People have faith. I like it. I like the way we're thinking. Radio. So all we'll see is an extra line in our profile and be like, oh, there's a tile binning shader running, and we'd see how fast it is. That's all we'll see. Radio. Let's go. We're looking about a bunch of people believe in me. He's some communist rebel dude that companies. Oh, that guy. Yeah, I know. I don't know what you're talking about. Yeah, I know. I know his picture, but I don't know of him. Yes. Right. If the stream crashes, guys, I'll be right back. Ah, good. Right. So just doing 9 spheres there is about 0.19 ms. That's quite slow. But it is doing some big spheres. So if we were to bring back those models instead, is that better? So here's the model. So we're just rendering a few models. The tile binning is dirt quick. It's very noisy, the result though, for reasons. But what's slow is the ray tracer now. See, it's about 3 ms, and this is what we're trying to speed up, right? So here's all of our balls, right? So the idea is we don't want big balls. If we have big balls, we get problems. Like we just spend too much time iterating over all the tiles. But these fit nicely into the tiles, right? But these are taking like 3 ms. Wait a minute. And then that one's taking 12 ms. Something's fishy. Yeah, big balls, big problems. What can I say? Speak from experience. Helped Castro when he was trying to help the communist revolution. No countries, fair play. Yeah. I need to watch a documentary. I don't know why this is 12 ms every other frame. I think it's something with my upload buffer. I think we've got some issues there. Rightio. So, a good thing to take note is this, but that's creeping up as well every frame. There's something fishy with these, with the upload buffer. I'm not happy with that. We might have to fix that. Should we wire in the ray tracer and then we'll fix the upload stuff, I think, because we won't be getting precise timings, and we kind of want to have kind of precise timings, right? So let's now modify the sphere ray tracer to take the tile binning tile information. So you can get your coordinate, which means you can map to tile, right? I'm too lazy to use brain, so I don't know why I've got the old UI render still. Oh, this is okay. This was here from when Yep. I was doing my video, which I still haven't finished yet. I was thinking about showing code, but then I realized it's probably not a good idea to show code at all. So yeah, we just want to get. Wait, do you get the tile index? Oh no, this is not a good one because the UI renderer works on a dispatch indirect, so it stores the tiles into an index. Oh, sorry, it stores the tile indices in an array which you pick out, and you just work there. Right. Yeah, so we pack. Yeah, we get a tile list. So we go based on our dispatch index, fetch the tile out. Right. Okay. So we can get a U32 times 2 tile chord. That would be U chord dot x divided by BC tile size, which I don't think we've uploaded just yet. So that'll round down to the nearest 1. Very good. So with that tile coordinate, we can then flatten out to tile index. So that'll just be tile coord dot y times by tile dims dot x plus tile coordinate dot x. Yeah. So now with that, we can fetch our array. We can get our base index for the spheres, and we can fetch how many spheres we actually have. We can fetch how many spheres that we actually have, right? So we can get a spheres count, which will simply just be BC tile spheres counts tile index, right? Then you can also calculate your base. Here it is. Base sphere index. Okay, so those are all the things you need. Now we just need to do a loop. So here's our loop. We go over all the spheres count, which we just made up there. And then we just say base spheres index plus, we're going into tile spheres and just putting out a whole sphere. Okay. And that's all we'll be doing effectively. I've just got to make sure we put in the correct buffers now into this new bundle constants. So we need the counts. I want to get rid of the spheres, and these are both read only, right? And we've got to make sure we fill those boys in, right? So we get rid of the spheres one and spheres counts. I need to get rid of that one. Spheres count needs to go from here because we get it from the buffer instead. And then we just need to synchronize on these two resources, which will be read only. And voila. Okay, so we need a tile size uploaded and tile dims. My mistake. Man, such a jam. Why wouldn't it load it? Oh, base sphere index maybe I need. Boom. So, here we go. The stream might crash. If it crashes, we'll be right back. But I think that is everything we need, right? There's an index that's happening in the slight wrong place. Hopefully the optimizer will catch it though, but you just want to do something like this instead. Yeah, because that could have been an out of bounds maybe. I don't know, maybe not. But yeah. Right. Let's see how this goes. Oh yeah, we're running. Okay, so we dropped down. Never seen my code crash. Oh my days, when we did all the UI stuff, this stuff was crashing left, right, center. Because we did a really complicated shader. Right, so what we're seeing here is we went down from 3 ms down to 0.11 ms for the sphere ray tracer. We're rendering 125 spheres, right? It's not mind-blowing numbers. And bearing in mind, we're doing this debug rendering as well, right? Which I should have probably disabled when we did testing the numbers. But anyway, it's quicker. And also, binning all these only cost 0.01, which is 4 times faster than clearing the whole screen. So I don't know. I was hoping that number to be smaller, to be honest, because I want to try and do hundreds of thousands of these. But we're going to put some more of these on the screen and we're going to see how, you know, yeah, we're gonna put a lot more load on it, and we're gonna maybe see if we can do this better. But yeah, maybe we'll do some commits and we'll have a bit of a play around. So we're just gonna put my models down, right? So here's the models. So first of all, let's disable the debugging. So we're not doing the bounds anymore. Look at these beautiful, creamy anti-alias spheres, eh? I know, maybe they look a bit janky. We need to maybe make that better. But anyway, they look beautiful, don't they? Now down to 0.09 ms to render those spheres. Okay. So let's make many more. So I want to make sure that with these models, right? Yes, ray traced, yeah. It's a custom ray trace on a compute shader. So if we do like plus sign t times, I don't know, 500. So this is going to go off into the distance and come back. My face. See how much that lagged when it went full screen. So that's going in all the tiles there. So that ain't good, is it? Yeah. My ass. So as it gets really close, it's really bad with the current way we're doing it. So that's something to take note of. Like when they're nice and small, this thing flies. So I don't know how. I don't know the best way to. Yeah, we could probably. So why don't we just place them in a sort of like, let's just go top to bottom and just cover the whole screen at depth 500. And we can always move the depth, right? So why don't we just say models, let's say, okay, let's do like a, if, I don't know why I'm, the whole point of these models is so we can just actually just spawn them anywhere and just have a whole bunch of stuff. So, well, maybe we'll just manually do these and just up their sizes. Let's up it to like, I don't know, let's say 250. Right, they crashed. Damn it. Oh. Right, we should be back. Okay. So like shut down my computer forcefully, and I need to stop doing that because sometimes it happens every once in a blue moon. But I was forced to shut down my PC. What happened? Why did YouTube just change? We had some sensible results before, but now it's changed. Oh, what is going on? Yeah, I've gone in incognito mode. I just don't want to be signed in. Yeah, usually we just get different results, but now. Where's the album I was listening to? The new one. They've just literally changed the website. What have they done? I hate YouTube so much, and I pay for it as well. It's really annoying. Right, so we've got GPU crash. Probably because we made like a ton of spheres. Did we overflow a buffer somewhere? I can't even tell you exactly which one we overflowed, you see. So, yeah, but I gotta be careful force turning off my PC because it could be like, oh, you sort of wrote to a file and then sort of corrupt a file. I've had corrupted files before, and it's not good. Like, a source code file will be like 0 bytes and be like, no. So yeah, we've got to be careful about that. So why don't we sort of undo this? That 250 was way too much, apparently. Let's check this in, and then we'll mess around with it. Right, we're back again. Oh, I thought I undid the code, which made it crash. So what did we change? So silly. Quite impressive that it crashed. Well, I don't know if it's impressive, Joe Omega. Apparently the driver's on AMD on Linux. I'm not sure about Windows. Already got that one open in it. Yeah, there we go. The driver's on Linux. If you do an out of bounds access, it will crash the GPU. Out of bounds access on the descriptors, crash the GPU. And it brings down your whole desktop. Also, if you run a shader for too long, it will also crash desktop as well. It's a bugger, basically. Oh, okay, they've put the website back somehow. They heard my complaint. So what do we change in here? Did we re-enable the... We was already viewing the bounds anyway. We disabled the bounds. Did I hit recompile? Oh, there's 4. Oh, I had the number 4 written in there. So it would have put some invalid memory on the half dimension side and made it massive. Right. I could see that being a thing. Oh shit, this better not crash. Let's do a sync. There we go. I've heard some people on Windows getting some experiences where it crashes, but not as bad as I get it. Right, so hopefully this doesn't crash. Okay, that was the problem. It's because we had a 4 in there, not because we had massive amounts of balls. We put a 4 in here and we ran it. That was why. Yeah, that's the reason why. So if I remove this, it would work. Oh. But it's 250 maybe. Yeah, 250 should be fine. Right, here we go. Right. So we're overflowing the number of tiles. Sorry, we're overflowing the number of balls that can go on that tile, basically. So it's 64 per tile, and this is the artifact you get if you overflow that buffer. I'm not sure about the hardware, to be honest. I just think it's... I don't know. So yeah, this is kind of a big problem. But what's interesting is the tile binning is still pretty quick. Right, so we definitely need some form of like culling, right? Because the biggest issue is, right, if we have spheres, like we should calculate how many spheres this is. Actually, before we judge this number, the tile binning. But yeah, the thing we've got to take note of is that the problem is, right, when you build everything out of spheres, the stuff behind it is probably going to be occluded anyway by the front, so we need to have some good occlusion system to really stop this problem from happening, where you have tons of spheres which try and get into the same screen tile, and they just fill it up. So we might have to solve that problem if we were to do this ray tracing route, right? But yeah. So let's explore. So I think like what I want to do is I want to explore this method just to see how fast we can make the tile binning and the ray tracing, ignoring the occlusion problem. And then I probably want to try it with a different method, which is more simple. I probably should have started with a simpler method first. That would have been a good idea. But I wanted to do ray tracing. Guessing that's your GP code, or at least you figured out an error. Yeah, no, literally, if you go if you only have your array of descriptors, if you index out of bounds on that, it destroys the G, it brings the whole desktop environment down. It could be a KDE problem. Yes, it could be a KDE problem. It literally locks the whole system. The whole Xorg, like stalls. That's probably the issue is X. I'm not sure though. Any percent computer only. Ooh. Yeah, I wonder how this looks actually. What do you do when your code grows very complex? Do you plan things in advance to solve problems as they arise? So there's two steps to it. Basically, there's a few things what you do. Try and solve the problems as simple as possible. Don't solve a problem you don't need to solve. It's a very hard thing to deal with, but yeah, that's what you need to try and do. The next thing you need to do is, when you don't know how to solve a problem, you're writing a bunch of code which is throwaway code, right? You're going to throw it away. Obviously, you can reference it to see how you're going to write the next version, but it's always throwaway. So you don't have to care about the architecture of that thing. You can sort of think of it while you're doing it, and maybe you can try stuff out. But the idea is you're not concerned about how this thing looks in the end, because you're going to rewrite it again, right? That's the other thing. And then I'm not sure what the third one was, but when you've sort of prototyped it for a bit, you got to then you plan it out, right? But yeah. Yeah, it could just be Windows, or it might not be. Yeah, it could be anything, right? It could be the Xorg, it could be AMD drivers specifically on Linux, it could be... I'm not quite sure where the problem lies. It would be nice if that didn't exist. It didn't exist, and I would assume it exists because not many people on Linux actually do game dev, right? Basically. So what are we putting a sphere down per? How big is the radius? 10. So it's 25 spheres cubed. It's 15,000 times 3. That's 46,000 spheres. And the tile binning is taking 0.2. It's very noisy, the result. 0.3, 0.1. 0.1, 0.3 ms. So that's 46,000 spheres. It's not bad. I want better than that though. But it's not a bad number. But you need like, ideally, you probably want to do a quick check while you're binning to be like, is my sphere occluded? And if your sphere is occluded, you don't bother running over the whole step of trying to fitting it into a tile. So that could obviously bring that number down as well. But you'll need to do like another pre-pass of a rough like depth pre-pass or something to solve that problem. But that's interesting. But the thing is as you saw, we got 25 by 25 by 25. So just for a tile, and we've got 3 of these guys overlapping. Yeah, it's quite easy to. When was it we reduce this to 8? That was 16 by 16 tiles. Sorry, pixel size of 16 by 16, right? Wait, we should can I want to save this. Git commit. So we just sort of say, implement sphere tile binning. Something like that. Sweet. So if we reduce the sphere tile size to 8, because the problem is that's 16 by 16 pixels. That might put more load on the in the binning code actually. It's a good test. Let's change these to 250 again. Right, we've still got, right, it put more load on the binning, way more load, and it's put them into the milliseconds now. But actually, it's proper noisy, the result. I don't know if that's just because of, yeah, the result's proper noisy now. And if we make, let's put it back to 16 again. What else are we going to do with this? Should we move them back a little bit further back, right? Yeah, it's made the tile bending a lot better. Obviously the ray tracing is a bit better as well. But yeah, so I think with the ray tracing you need a good occlusion check, because if not you're just going to bump into these problems all day. Like you can up the count, the number of slots you have per tile. Where's the shared? So we've got 64 right now. What happens if we up that to 128? Like you've got 25 or 25 or 25. Like maybe that fits just enough in. No, not even that. What happens if we did 256 per tile? That's a lot of memory, probably. What was it? It's 160 times 120 tiles on the screen. It's kind of a low res. Oh shit, that's a bad number. No. Times 256 times by 8 bytes. Wait, 8 floats. So it's 8 times 4. It's about 150 meg for all that. We can obviously lessen it by keeping indices instead. So you're still getting problems, and we also 256 fit spheres per tile. I also started a smaller second side project, CPU emulator, starting with RISC-V. Sweet. Yeah, those are always fun, right? Like doing that sort of stuff. What's the purpose? Is it just for a bit of fun, or like a nice small project to do? Or are you trying to learn RISC-V, something like that? Hey there, Moade. Hey. Nice. FUN. Fun. Very cool. So we can't really, I guess we can debug visualize these tiles. It's not, we gotta just render some UI on top of it, or behind it. So there's our tiles, right? Effectively, we're using the same sort of tiling system. So these guys, again, even those, there's a problem. Some other problem, surely. I can keep up in this number, and maybe we can see if, let's do 512. I mean, we have the memory. I can't. I think we get in some other issue. Shall we reduce the number of... Say we reduce it to 100. So that's 10 spheres, 10 by 10 by 10. It's still having problems on that corner. I think there's some other issue going on here. Like, if you just overlaps, like... Because there's no way that we're filling 500 spheres going through there, right? Or maybe, because the boxes are a little bit bigger, aren't they? Thinking about it. The boxes are a little bit big. Eventually you want to do x86, but it has to be something like... There's something like 500 registers and 200 instructions. Oh. Yeah, you could be right with the Z fighting thing. So if we just move this to like... Just made one of them in front. There you go, ain't got it anymore. Oh, 9,000, a bit too far. Like little pixel sized. Alright, 900. So, yeah, that solved it. Right, so it's a bit of a Z fighting problem. There. Right, so if you had a good occlusion culling somehow, right, then in theory both of these steps could be sped up. What are we rendering now? Did we up it back to 250? We did, didn't we? So it was 46,000 spheres. You know, I don't know how small I want these spheres, right? Like, and yeah, we had a problem where if we moved them super close to the screen, it was dog slow. Yeah. So let's move these a bit apart. Let's say 600, 600, 600, 600. How did that go? Right. Let's get a better view of these guys, isn't it? What else did I want to do? Right. See you in a bit, John Mega. Have a good one. Have a good start to your week. See you soon. Yeah. So the thing that I'm not too happy about, well, something that I want to keep I want to think about on the side, right, is these numbers differ greatly. They have a big high and a big low. So yeah, we could try and minimize that with whatever solution. Yeah, so the big difference between sort of what their min and max is. So they're quite not very. They vary a lot between frames, which is not probably ideal. Right, they spike a lot. There's probably something to think about. So we could think about some other methods on how we could do tile binning. We're fitting a lot per. That's 512 again. Let's go back to 64. Is that still enough? Right, that ain't enough for that. So that was covering. Right, okay, so it did 128. 256 for this one. Right, 256 seems to work for this one. How many models? Right, 250. It wasn't 250. Yeah, it's 250 divided by 10. So that's 25. Okay, so right. So I think what we're going to do is think about different ways that we can bin per tile. And say if we've loaded now. Right, so we go into our shader and enable this guy. This is going to draw the screen bounds of those. Right, it's a bit too many colors in our face. But these are the boxes you get in. So there is a bit of overflow on them. Oh, sorry, they're a little bit bigger, right? So what we're going to do is we're going to play a bit of a... We're just going to reduce the bounds. We're going to times it by like... let's keep it enabled for now, the debugging. Actually, no. Yeah, so we're going to see like how much better can we realistically make. So the sphere ray tracer is in about 1.6. If we were to have a smaller box, how much better does that really make it for us? So this half dimensions thing. If we do half dims, do times equals 0.9. So we scrape off 10%. How much better does that make it? So that's knocked off. That's made about 1.5-ish. So I guess if we take it to about 1.75. 1.4. And we're starting to see some glitches where thing's been cut off now because our bounding box has been made a bit wrong, right? So that's interesting. Yeah, so definitely, obviously, the further we put it back and the smaller these things are, the better it is. So the problem with the tiling thing is literally like the size of these really matters a lot. Where is it? Tile binning. Yeah, so the problem with the current solution that we've got is as soon as this sphere becomes absolutely massive, doing this long iteration and doing an atomic add into these tiles is very problematic. So the other solution we could do is we could mimic the UI one, where we blast them into chunks and then we blast them into tiles from there. So the UI one has a two-tiered system. So I'm not sure. Yeah. I'm not sure how good that is though. So if we render the UI again, let's just put that on. This is doing like 0.01, 0.02, and that's just doing draw. Look, these are draw things here, draw commands here. I don't even know how many we have on the screen, but I don't think it's nowhere near the number we have. Probably great to get that number. Where's the draw commands count? This one. Core print. Right, I only got 192 boxes that we're sorting. So, add those two together, it's about 0.03 ms, right? Times that by 10, so that's about 1,000. Goes up there, times by another 10. So, about 19,000, it's going in over here. When we're already doing many more. Like, we're doing 46,000 at the moment. Yeah, 46,000 for this one. And it's only 10 times slower. And we're doing way more data. So that's probably not a good method to go with, right? The UI one is definitely not a good method to go. The binning is not good. But we've got to solve the problem where what happens if you get big spheres? And how do we keep it so the spheres are small? And then if we can keep that, so if we can do that, maybe we just have a limit on the sphere radius and it just can't get above 8 or something. And then that just solves the problem. We just get more holes. It's not, yeah, it's 25 by 25 by 25. Yeah, times 3. Because there's 3 different models. Yeah, it's because the radius is 10 right now for every sphere. So it's 250 divided by 10, which is obviously 25. And then it's 25 times 25 times 25. Times by 3, 46,000. Because there's 3 of those models. Each model is 25 by 25 by 25. And we've got 3 of them. So I'm thinking what happens if we just put a hard limit on pixel size? How big can this... right. How big can this thing be per pixel? So you have a sphere and you say, so you've made your sphere and you've got it in the world, and we could probably say CPU side, should we do the clamp or should we do it GPU? So you do pixel size at depth and you can clamp it to like we can do some things, right? We can say, but we've got to do it in two places, which kind of sucks. Oh no, we're pasting the sphere in here, which means we're modifying it. So we could essentially just say, right, it's quite sketchy, but let's try it, right? Sphere, pixel size at depth, pixel size at nuclear plane, multiplied by sphere dot center position dot z. And all you're saying is just saying, right, sphere dot radius equals min sphere dot radius sphere dot radius pixel size at depth times by, let's say we've got a limit of 8 pixels that you can take up. I can't even move the camera. This is not 8 pixels though. Oh. No, that's a radius, isn't it? 16 pixels. There we go. Well, that is... So this is a way we can solve the problem, is we can basically just clamp it. So we're getting a lot of shadow here. That's the reason why it's dark. Not because... Well, yes. But yeah, so they are rendering properly. So this is how we can solve the problem of things getting too big. We can just clamp it like that. And we'll just see... But then we'll start seeing space between the balls. But that's probably fine. So when you start seeing space between them, that's not a bad idea actually. So if we move them closer, so let's just get a nice sine sort of distance modifier on it. So if we go, so if we say, wait, where is it? The Z, yeah? We'll do a sort of a plus sine t times, should we say 350? That looks a bit sketchy, doesn't it? Oh, it is. The effects. My eyes. So if things get too close, you're getting a lot more space. Yeah, so maybe it's not a good idea. I don't know. It's interesting though. The way you solve the problem with the performance is you just clamp the spheres to a certain size. Yeah. Not sure. Right, I need another iron brew. I need to tackle this. It needs some iron brew juice. I'm also gonna get a drink of water as well. We gotta do. Right. BRB. Right, welcome back everybody. How's it going? So, got myself another iron brew. Okay. So, what happens if we make this sphere? What happens if we make the sphere limit go back to 8 again? 8, so 16 pixels. Does it look better when it gets closer? Trying to look at the performance numbers as well, I don't think it's too bad. So we don't let them grow. We only let them grow to a certain size. So if you have lodding, this is not so bad, right? Because you can have a high detailed model with a lot more spheres. This is only 25 spheres, right? So maybe if you get so close to a model, you'll see through the spheres. See, if I didn't do this, the spheres would all be the same. They'll be bigger, right? See, let's up the size a little bit. Let's say they get 32 max. So that's 64 pixels they get. So 64 pixels is actually only 4 tiles or something. Yeah, so maybe we can make it a decent number where it's not affecting it so much. When when your model gets too big, in your point of view, it just lags you. Yes. So this is the problem with the current tile binning solution. So the reason why it's a problem is because when you do the tile binning, right, we do one thread per sphere. So this is where we can reorganize this today, right? We can try a different solution. So the current one is this code gets run in lockstep across 32 threads. So you'll keep iterating over this so long as there's one thread which is still going over a sphere. So if you happen to get bundled with a sphere, or if you happen to, you might have a bunch of small spheres and then like one massive sphere which covers most of the screen, then you start getting into problems where you spend more time iterating than you need. So a solution is to bundle all the big spheres together and all the smaller spheres together, but then you need to have a pre-pass which works that out. That's one solution. The solution we're looking to now is just putting a max size on it, so we keep it very small. Instead of clamping, making the spaces bigger, could you change the way the binning works when it hits a certain threshold? So what you're saying is like, say if it goes bigger than a certain threshold, put them into different. So you maybe have a sort of a larger tile, maybe, or something, and it would bin it into a bigger tile. And yeah, that's another way you can have it, is have different layer sizes of tiles. You could probably have chunks, and the chunks will be massive, and you just put the big ones in there rather than iterating over the smaller ones. That's another way to do it. And then you'd have to check two different loops in the sphere ray tracer. But then you'll be filling up less of the. Yeah, it's not a bad idea. That's probably a different way. That's probably a good way to do it. And then you won't have to probably clamp, right? I liked the idea of the clamp though, but it just visually doesn't look good, unfortunately. I don't think these end up reaching it actually. Can I remove the clamp? Yeah, maybe these. Yeah, these don't get close enough, I think. But yeah, you can maybe just go, hey, if the bounds is this big, just go up a layer and go into the big chunk layer. Yeah, no, it does seem like it. Like, yeah, that seems definitely like one solution we could do for sure. Just have larger tiles. Um, it definitely seems like a solution that we can do. Just bin it in those. Um, right. So we have big tile, little tile. That's one solution. Yeah, so the other problem we're trying to solve is so yeah, so what's the biggest problem? I think it's just that really. Also the speed could probably be better. So is there a way we can rewrite this where we can tackle both problems with speed and um so you're currently doing one sphere per thread. Instead, you could make right, each sphere goes over all of the tiles it could possibly overlap. Um, so I wonder if you sorted the spheres. Yeah, but they have to sort them. No, it's not. I think that's an ideal solution. Ah, son of a Viking, how's it going? Thank you for the raid, sir. Appreciate it. Welcome, Raiders. How's it going? Currently working on a game without an engine. Rennet C. Um, currently rendering a bunch of spheres on the screen using ray tracing. We're just trying to make this go fast. So if you have any questions about this project or you know, or anything about Program Ready, just ask away. I'm right. How's it going here? Yeah, it's not going bad. We just got some tile binning working today. Got some visual artifacts and stuff. We're just trying to solve. Just trying to think about this really and solve it in a good way. Yeah, it's about it. We're just trying to see how many spheres we can render on the screen because we're thinking about building everything out of spheres basically. Yeah. Yeah, it's not bad. Not bad progress today. Much better than last stream, that's for sure. Just trying to figure out what we want to do next, really. But yeah, how did your stream go? So yeah, so I think the solution we've got in terms of like the way we go over the way we've got our sort of, each thread has a sphere which goes over just the minimum bounds on that. It goes over each tile and puts it in. I think that solution is good. Yeah. I don't think because you could go over every single tile. Wait a minute. Yeah, I think that's not so bad. Yeah, I'm not sure there's any way we can change that. Right, I think the next thing I want to do is like, let's chuck more spheres at it. So every single one of these that we add, what are we adding again? 25 by 25 by 25, isn't it? 15,000. So we're at about 15,000. So we're at about 45,000 right now. So we just did this. And then sort of like made that positive y instead. And then maybe move this one to the left. And then didn't bother changing the sign here. Oh, I didn't bother changing the Z. Then we do this one more time. Do it to the right, the left instead. So that gets you 15, 30, 45, 60, 80, 100, and 5, 120. Now my 15 times table is obviously the best. So there's 120,000 spheres. Let's roll. Maybe we shouldn't do them. All right, let's do it. Screw it. Let's go. Why are we not seeing... Why are we not seeing all of them? It was alright, fitting off didn't help though. Yeah, I get you, man. Difficult streaming sometimes, especially when you're tired. Yo, Gmos, how's it going? Yeah, lots of magic numbers. We're just prototyping, so lots of just jamming code, you know? I see Parser can parse that. Well done. Awesome stuff, Toby. Look at you. Got that function pointer going. Oh, my man. But why did you need that? I think the cytokines were so small. Oh, yeah. Not really. I'm not a fan of maths. But, alright, here's what I like about maths. I get the joy out of trying to do something and finding its simplest form, right? But also I can't do it. like, when I read people's maths, I'm like, okay, that makes sense. But I can't get to where they got. I can sort of like see the bits they've come up with. I'm like, okay, that kind of makes sense. I can sort of get it, but I just can't get them myself. That's where I'm at with my maths. But yeah, I can tweak stuff and I can be like try and reuse things that I see in other places and that like, but you know, at the end of the day, I'm not the best. Why can't I see all these balls, man? Where are my balls? Have I got overlapping balls? I don't think so. All these numbers are different. We should be seeing different numbers. What's going on? Oh, we've run out of the capacity of balls. Because we're 120 odd thousand balls. We've got 65,000 balls. Exactly. There we go. Got enough room for my balls now. Oh yeah, look at that lag. So the sphere ray tracer is like too many balls in my face. So it can't deal with all these balls. Ain't good. Why is the sphere ray tracer so slow then? Right, because some tile... Okay, this is a good test. We're covering every pixel. Right, we need more. We need more balls. Right, let's keep them coming. So... 3... 6... 7. Right, let's look at my maths is. So we want to do... 600. So yeah, every single time we add a new model, it gets a different color. That's the beauty of this code. You see they're all different colors? Wait a minute. Where's my bottom balls? You know, ones at the bottom. Are they too low? What? My high balls, my low balls. Where are they? Oh, days. Oh, okay. The balls got cold. That's it. So let's just do 6. Put 6 there. There we go. So we're proper lagging now. I would expect this is more than... It's saying 6 ms. But that should be 60 frames a second. So clearly the CPU is lagging. The CPU cannot keep up with all these balls. So this is why we want to use the GPU for stuff, because it's obviously way better. Like the CPU is like, I can't handle all these balls, right? It's trying to do that, and it, you know, maybe. Right. Here's my CPU. Wait a minute. Activity monitor. Wait, I need to do the thing where we sort of go. This one. Oh yeah, 90%. This one. C core 4. Okay, it's jumping all over the place. But there's a 90% some. There you go. There it is. 100%. Gotta chase it around. Okay. So we're CPU bound with this thing. It's the reason why it's lagging. But we're getting, right, for about... so this is why we want to move this to the GPU and have a concept of a model. But the concept of our model at the moment is just a rectangle, right? But we'll make that, you know, we're not caring about this at the moment, but eventually we'll just have model and model instances, and the GPU will just produce all of the instance information, right? And that's fine. What's C version of Ryan? C11, because it's got some nice little bits, but you know, you don't really need the stuff from C11. Just it's got a few syntactic niceties about it. Like for instance, you can use a union which doesn't have a name inside of a structure, so you can have like an anonymous union field, which was kind of missing, and it's great. That's probably the only reason why I use it. But yeah, C99 has got a lot of the good stuff in it. And C23's got some good stuff, but they also did some silly stuff like null pointer T and stuff like that. Yeah. I feel like this ball rendering is going to be tons of little funny references to it. Okay, so let's what do we want to do? Should we not bother with a sine thing for a second? Let's make t. Let's freeze time. Okay, so what we're seeing from these numbers with the tile binning is we're seeing them sort of... Right, they've got a little bit of spikiness to them. Yeah, they've got about 0.05... Sorry, about 0.5 ms sort of high and low, like, difference, we're going to call that. And then the ray tracer is about 4.9 ms. So, why is it so slow? Is the question. Like, okay, so what are we... So dealing with 100 and... Wait, I forgot now. It's 9 times about 15. Well, 25 times 25. Yeah. Times 9. 140,000 balls. Yeah, so I'm trying to find like a good number of what we can work with, and make this as fast as possible, basically. So every pixel gets a list, and the list is 256. That's not good, is it? So we wanted to make it 64 ideally, the max that they look over. That's still not reduced it. It's reduced the tile binning, but the sphere ray tracer is still taking... Did it reduce it? 4.9 ms? Okay, reduce it down by 1 millisecond, right? So I guess the number of the spheres is probably not... I definitely want a lower number. We're going to solve that problem with occlusion culling, I think, which we've got to look into later. So we're going over all the spheres in a... Right. So we could preload. So what we're doing 8 by 8. So we could preload them into LDS or something. So the spheres are being shared between the 32 threads. So we go over all of the spheres regardless. We don't early out. So this is part of the problem. So part of the problem is we don't early out, and we go over every single sphere, and we test it. We do a ray test. If we miss, we do this code to try and get quote-unquote free anti-aliasing, but it's not free. It costs. So we disable the anti-aliasing. How much does that get us? So that knocks off 1.5 ms. So this is all... Can you see how horrible this looks already? All that aliasing, it's really bad. So this cost about... Yeah, it costs, right? Doing this still. So one thing that we could do is we go over every sphere that's in a tile. We could go over all the spheres, do some sorting, and then we can do front to back alpha blended spheres, and when we hit a fully opaque pixel, we early out. So we're going over all the spheres anyway. So we go over all of them and sort them. We need to sort them by... we're also calculating a color. Yeah, this is not really an optimized shader. This could be done... So every time we hit, we calculate a color. That takes time. It's not free. What else? Yeah, so what do we need to do the sorting? Well, you kind of probably need to do the trace, right? So you go over, do the traces, get them into LDS memory, and you can multi-thread that, right? Wait, no, you can't. Um, Wait a minute, I've just thought maybe it's not easy to sort them. No, you probably could. So you just do a sort of a... Yeah, I think it's possible. You can always take away the radius and then sort that. Um, huh. Yeah, so you go over all the spheres. See, I'm not sure about a good sorting algorithm. But yeah, you can use... Each thread can process a sphere, rather a different sphere. Yeah, each thread can process a different sphere, put that into LDS, and you would practically get that for free. Well, it would happen like 32 times quicker, basically, wouldn't it? In effect. And then you're also preloading this into tile memory, maybe. No, into LDS memory. I don't know, maybe get a boost from that, I'm not sure. But yeah, definitely not calculating this color every time. There's going to be a big difference. So maybe should we just do that and just see what happens, right? And then we'll do the tile sorting, I think. That'd be a bit fun. What condition for this early out going to be? Right. So currently we just trace over. So we got a screen array. We go through the screen, and we'll just go over every sphere that goes through that. That array is that the array might touch within the tile. Right, there's like a tile here, screen tile, and we'll go over every sphere which kind of overlaps with that tile. So if we sort them, and then we can do front to back alpha blending. When the alpha becomes fully opaque, we early out. Yeah, if it's opaque, we want it. Yeah, if it's opaque, we're done. We can just early out, right? Because you have the full color. So that way you can do alpha blended spheres, right? And you should be able to early out as well. So let's avoid doing the color calculation. So we're just going to store probably a hit normal, closest hit normal, closest hit color, closest hit normal. Closest hit color. S.color. So we've found a hit. Closest hit normal, closest hit color. So we set that there. This is where we do the near miss of alpha blended stuff. We do a calc color. Why do we do that? On the alpha blending. Right. Old near miss. E32 near miss color. Near miss normal. So we're using more VGPR probably, doing it this way, but it should saved in the calculation. So yeah, this one's saying that we've already had a near miss. Make that old near miss a hit. Wait. Old near miss has been replaced and is closer than the closest hit. Replace the closest hit with the closest miss. We're about to overwrite, yep. So we found something which ends up being a closer near miss. We won't have to have this code when we sort it, I think. No, we won't have to have it at all. Closest hit color. Closest hit. Normal. Something like that. Right, so we calculate the normal here. This would be the closest hit. No, this would be the near miss normal. S color. So we want to take this, put it down here. Oh, what is this? Near miss SS. Near miss distance in screen space. We need that. Depth is less than. Right, so we need to calculate that once. Closest near it. Oh, shoot. Right, we'll just keep this. Bit of a rewrite going on, I can tell. What the matter see is you can tune at any time and understand what the code on the screen does. So I can tune anytime. Oh, tune anytime so the code does. Excellent. Awesome. Glad that's true. Oh. Yeah, it's difficult reading people's code sometimes. Yeah, C is a lot easier sometimes, especially when you keep things simple, you know. But yeah, I guess it's a little bit hard to tell, are we on GPU, are we on CPU? But if any of you guys ever get stuck on that, you know, when the shaders file, therefore we're doing shaders. That's one way to do it. That's one clue. Well, where we're at. But yeah, haven't got any templates or overloaded functions or anything like that to deal with. So normal than the color, and the rest just goes. So we can just say, so it blends the color. Near miss color. Near miss normal. Near miss color. Near miss color A equals near miss distance screen space. Right, it's just saying near miss color A is less than 1, less than 0. Let's start off at positive infinity. Sweet. I think that should work then. Righty, yeah, let's try this out. So what we've done is we've reduced the amount of times we call this calculate sphere color, right? This ends up being, like we call it per sphere, which doesn't need it. It does like a normalize, it does this thing here, which, you know, is a bit of work. It does a PAL, converts from sRGB to linear space. So I don't need to do that all the time. Right, let's give us a go. I don't know how much we saved there. We saved 0.5 ms because it's going to about 4.9, wasn't it? It's going to 4.9 ms down to 4.5. So it wasn't as much as I was hoping, but it was something. Right, it was still considerable percentage-wise. So the next thing to do is make the music play again. Right, so this ended up taking up some time. Probably to do with, so this is the anti-aliasing, right? Yeah. Right, I think we should pre-calculate the, yeah, let's do the sorting thing. That'd be fun. So we need to make some LDS memory. So let's make some LDS memory. So you just do this global variable with special dispatch group thing. So it's basically like static, but it's like a special one for the HCC compiler to say that it's going to be shared across every thread in the thread group. Wait. Yeah, every thread in the thread group. They all got the same spheres. Excellent. Yeah, usually read the tab, but you're not making it easy HCC, which is a great problem to have. Sweet. How often do you order out? Well, food wise, I don't get much takeaway, to be fair. Like we go every Friday to Nando's, like me and my wife, and now the baby. You know, it's a nice cheap sort of way to go out. But the place near me is sort of temporarily closed down for refurbish. So we're probably going to skip it for this month. Yeah, typically every Friday we go out for a meal. That's about it. Or whenever there's a birthday celebration, which is always comes up. But yeah, I don't typically get KFC in that. I especially don't get McDonald's. No McDonald's. Thank you, Tyler. I love you too, man. Maybe I'll extend your shader files with .csl when I choose HTC C shader language. Not bad. Yeah, it's got to get the syntax highlighting to work, you know? Do I watch anime? Anime. Hmm. Not really. I did watch. So I read Attack on Titan manga, and then I watched part of the anime. Um, I used to watch a lot of anime as a kid. Um, but not probably. I didn't watch Dragon Ball. I mean, just like sort of, Western anime. I watched like Avatar, Legend of Aang, that sort of stuff, right? That sort of anime. Not the Japanese one. I'm sorry, Ty Beaver. What sort of anime do you recommend? Damn straight. Welcome, welcome. So this is shared between a group. So when we do this by this, okay, gotcha. Right. So we want to write some. So right. So we've got about like 8 by 8. Wait a minute. So you're launching this many groups. Um. Yeah. So you got this many groups of that. Okay. So effectively, you want to preload. Yeah. So you want to do a nice little loop. Over all of the spheres. Well, you've got them here, isn't it? Spheres count that this tile has, right? But you're not upping by one. You're upping by the number of, sort of like a const. We'll call it something like, this is the wave, wave threads count. One of these guys, yeah? So we'll skip by that. So each, this is going to be like a base index. Each thread, so each thread is going to come into here, 32 threads in lockstep. And it's going to get its index, which is going to be base index plus whatever SV. So you need to work out your thread index. That would be, so we can calculate that quite easily. See, the problem is you don't want to exit out too early. So you can run all this stuff. So right away when you start up, you kind of want to run this as soon as possible. So you can use all your threads. If you early out in some of your threads, you're not going to be able to take advantage of all of them. So your thread index is going to be y times 8. Okay. Plus x. So that'll get you a number from 0 to 31 inclusively. So then you say plus thread index. So now what we can do is we can preload a sphere and we can do a bunch of cool stuff. So sphere index, okay? So you got yourself a sphere, S. So we can now work out the sort of ray origin to sphere, like so. Then we can work out how far this is from the camera, probably in squared space, I reckon. Something like this. So this would just be depth squared. Now this isn't exactly the depth that we want. So we should probably take away, this is going to be rough, but we should probably take away squared radius from it as well. I'm not sure how correct that's going to be. We should probably get out the blackboard here. Your Name is a movie. It's great, in my opinion. Is there a film called Your Name? Or are you saying my name? Oh. Right. I'll leave that tab open. You're banned John Blow's chat. Fair play. How did you manage that? What did you say? Did you say I love Rust? All the GH Ibli, Olga Hibli, I don't know, stuff. It was nice to watch the wife. Sweet, I need good stuff to watch. What is this? Oh, these sound familiar. Right. Oh, it's the animation studio. Right. I see. I see. Right, I'll keep these open. Thank you. Any other suggestions? Chuck them my way. So, spheres, balls, what are we going to call them? We are doing something where we have a ray, and we're taking the ray to the sphere, and we're saying, right, I'm not sure how good this is. We're saying, hey, that radius you've got. So we've got this in squared space, the length of that, because it's just cheaper. Then we're saying, well, this radius here, take that away from it. Squared distance. That's probably safe when comparing against other spheres. I imagine so. Maybe it's not. I don't know. Let's hope, because it's cheap. I like cheap. So there's your depth. And that's what we can use to sort them by. So now we need a sorting algorithm. So all we need to have is some local shared memory where we can dump the spheres into here. Yeah, we dump the spheres into here, and then we can have. See, I'm not sure how good it is to pull in the whole sphere structure again. I'm not sure how good that is. So we'll store a maximum of sphere per tile cap, whatever that is. We should probably bring that number down to like 128 maybe. And then we probably want to have like spheres sort indices or sorted indices, and these just be a bunch of indices, right? That we can just go over. So that would be interesting. So we can build up the spheres array quite easily. So we just preload it into here. You know what? Let's not preload the spheres in. That's dumb. Sphere distances, right? Less memory. I think it should be better. So we'll just do some of this, right? So you just pre-calculate the distances across all the threads. So you just be like, oh shoot, yeah, sphere index equals depth squared. Um, so you've sorted those out. You've got to make sure that you don't go out of bounds as well, right? So you need to also check and say if sphere index is less than, and then you can do all of that, yeah? So if not, you just get a load of rubbish. Rightio. So that is sorting out the distances and that, but you still need to sort it. So let's find a way that we can sort using or leveraging the fact that we can do 32 checks at a time. Hey, Katsumoy. I'm sending all my struts to the GPU and I plan on adding more functions to it. Right now, when the size of a strut is 100 bytes. Consider add 20 more functions. Is it okay? Imagine if I send a megabyte strut. Well, it depends. What is your strut used for? Right, it's fine to send information. Yeah, you can have a big buffer with tons of stuff in it. It's more about what is your access patterns like. You know, say if you have a massive structure with a bunch of like constants in there that your CPU just up. You know, you got like matrices in there and little floating point numbers, which is to do with like the whole game. They just want to reference sometime and pull them in. That's probably fine. You just want to make sure that GPUs work in a very similar sort of fashion with CPUs. They have cache lines, right? So if you read stuff nearby, it's better. And also you don't want to write to the same memory locations across many different threads. Like you can do it, but just be wary that you will have a bit of performance impact, right? Like GPUs are pretty good nowadays. You can send tons of data to them and that. You just have to be concerned on how you're using that data is all, right? That's about it really. Do any resources about IR optimization? Oh. I don't really have any actually. Yeah, I did a whole bunch of research on how an IR should look and or what an IR has designed an IR. I don't really get too good resources from that. Yeah, but I haven't really done any IR optimization. I've just thought about it and how I would do it is all. So I don't really have any good resources on it. But yeah, if your IR is SSA, single static assignment, you can kind of think like how some optimizations can go. But yeah, sometimes you have to build a call graph up and then sort of use that call graph information. Yeah, there's but yeah, sorry, I don't have any resources unfortunately. Then we get a chance to go and do it. Where's all this rainbow magic here at the edge? What have we done? Did I blow up my anti-aliasing? Oh, I bugged my anti-aliasing, didn't I? No. I said less than 0. What? Oh yeah, I reduced the number of these guys. Let's put the 256 back. Did I bug a anti-aliasing? I did, didn't I? Oh, it's looking anti-alias to me. Yeah, it's lagging because we're CPU bound, not GPU bound. Although the GPU one is slow. I'm not liking the speed. Corrida. Unfortunately, the zoom tool is not good on KDE. It's like, yeah, we have a zoom tool, and then also, oh, it's blurry. Yeah, those are, I don't know what to call it. Oh, they're aliased. Anti-alias, aren't they? I don't. Yeah, we get some transparent. I'm not sure anymore. Yeah, we are. If I turned it off, we'll be able to tell. Let's turn it off. First, I should be able to send my strut to the GPU with all the functions in there. But I don't have anything to render, but the game data like summons minions. So I'm not sure what you mean by send all the functions there. Like, yeah, you can put a lot of. You can program the GPU and give it tons of. Yeah, you can fill, like, you can have, tons of different little shader programs and functions. It's fine. People do a lot of GPU driven stuff nowadays. The only thing you got to be aware of is when it's done on the GPU, it's difficult to get that information back. Like if you do logic, you should only do logic on the GPU, which you use to sort of drive rendering, really. Like you can do like game logic in there if you really wanted, but it becomes a bit of a problem when you want to sort of save some of that stuff back. You got to send it back from the GPU and all of that, I would just be a bit skeptical of doing that. Like it could be a good thing in the future. You get a lot of performance, maybe, but process all your entities on the GPU. But I'm unsure. Yeah, can you see it's hard at the bottom here, and it's softer. There you go. Yeah, so we've got some anti-aliasing. Yay. Also, if I say with anti-aliasing, does it? It's we don't get the pretty colors, which means I've buggered the anti-aliasing up a bit, which is not a big deal. It's gonna happen. I'm gonna be fixing. I'll be sort of like sorting out the code anyway. Should be able to find the problem. Just figure out what it is. Right, color. Found hit is true. Oh, you're doing a near miss, but you found a hit, but you've not got a proper color. Something like that. Yeah, I think another problem is if you've got a near miss, you've set this to true. If I disable that. Yeah, we're not getting the yeah. So the reason why I was getting that multicolored thing, yeah, is because we were saying, oh, we found a hit, and then it's like processing uninitialized memory. It's just getting multicolors. That's fine. Cool. Right, let's do the sorting code some more. Oh yeah, sorry, and you basically had the right sort of track to take there to solve the problem. That's good. So what the distance is in an array now. So now we can multi-thread sort this thing. I just don't know how to sort it. There is that bitonic sort. Um, I don't know, H+L. Oh, for crying out loud. Damn you, Microsoft. I want to see if there's a simple bitonic sort, because I've heard this one can work well. It unrolls 28,000. Your code's going to get big. Right, description. A bitonic sort must eventually sort the power of 2 ceiling of items. One does this many. Right, so we do. This has got to be power of 2. Okay. Because of this, null items must be used as padding. Right. That's fine. Pre-sorting does 2. It depends. Null items as needed, and does the initial sorting for. Right. So null item. Okay. So they did this sort of filling here. Oh, okay. What's the thing on the Discord you put in? Oh, sweet. I'll take a look. Thank you. It's simple and works well for small to medium-sized data sets. Right. Where the number is sorted is power of 2. So ours is going to be kind of quite small. So it's not going to always be a power of 2, but yeah. Hopefully we have less, around 64. We might have less. Paradox sort. Non-comparison based. Particularly for larger data sets. Yeah, so I'm hoping that we won't have too many items to sort, so maybe the algorithm doesn't matter so much. Yeah, thank you for that. That's good. Yeah, so you split them into buckets, isn't it, with the radix sort? Right. Yeah. I might just try this bitonic one and see bitonic. See how we go. Oh. Yeah. Hopefully it's simple. I hope it's simple enough. This is my hope with it. So it's gone over the rounded number, right? And they fill up with the. So yeah, there's the power of 2. So you do k divided by 2, right? Index is insert 1 bit. Sort key is A. Should swap. Should swap is probably just a comparison, isn't it? Oh, so... Oh, but probably in that header file. Sort common. So if it's not a null item, right? So if A is less than B, it's going to swap it. So where's... So you're going over 1024... So there's 1024 threads running. Well, not in lockstep, but yeah. There's... Right, so 1024 threads running, some in lockstep. So... Where do they get their unique thread? Group start. GI. Aha, GI, that's it. Is it? No, it's group index. Flattened index of the group, isn't it? It's not the dispatch one. And it's white screen. Wakey wakey. Yeah, it's on the dispatch index, isn't it? I forgot what they call it. Dispatch thread ID people usually use, isn't it? Yes, right. Yeah, so I think this is the one they use in GI. So there's your individual. No. So I can't understand how this thing works. I think you need another sample, not gonna lie. This one's not the best. Bitonic merge sort in. Oh, where's some code? Do flip. So there's a swap. So that's just getting the thread index. So it gets the 2 indices to possibly swap. And it'll swap them. If one is less than the other. That's how most of them work in it, basically. So the problem with us is we've got distance. Right? Yeah, so we should probably cram the distance inside the key, maybe. And then we can just sort it. Yeah, I think that might be a good idea. Do disperse. I'm not sure what this does. Wait, so disperse, is that kind of similar? A little bit different. Right, so it does a flip. Not sure what this does. This does. Yeah. This one doesn't look too bad to implement. Right, let's give a bit of a read through. So if this algorithm works really well to parallel hardware such as GPU, right, in the diagram, each worker thread is shown as a vertical line with the start and end points. All color blocks are marking indices of the current pairs of sortable elements. All color blocks which are the same column form a step which is executed in parallel. We can see the diagram, the number of threads per step is constant, and that is always n divided by 2, with n being the number of sortable elements. This might be a bad example, an example there. Sweet. Ooh. Is this one of your ones? Right, so do the compare and swap. Right, so you got your elements. Plus k, k is counted by 2. Right, so you're splitting each, yeah, in halves and halves. Right, it's recursive though. But I see, so they probably do it in a non-recursive way. And then do a merge. Right, so you're doing like a binary split, and you're sorting. What are you sorting in the merge? Right, so you keep calling down until you keep subdividing until you land on the 2 that you need to swap or something, and then okay, it's a recursive one. Then you're swapping those. Then you come up, and then swap the result of those. Yeah, I see what you're doing. Then you come back up again and sort the 2 next to each other. Come back up and sort. Okay, I get the idea of that. That makes sense. So this one is probably doing it in a non-recursive way. Before we figure out the sort index pairs for each worker thread based on each thread's execution step and thread number, let's step back and look at the diagram through squinted eyes and see patterns emerge if we group smaller looking blocks together. So I'm not really sure I fully understand the diagram. Then each worker thread is drawn as a vertical line. Each worker thread. Okay. Well, I guess I see a pattern, right? Oh, it's run as each worker thread is run as a vertical line with start and end points making the indices current pair sort of items. All colored blocks, which are in the same column, form a step, which can be executed in parallel. We can see in the diagram that the number of threads per step is constant. I'm not quite sure if I get it still. Because you've got start to end points, right? And these sort of colors are not colored in. Right, let's just keep reading on. Green block doubles in height until it reaches the total number of its elements. Let's call that a block flip. Yellow block, after each green block, there is a cascade of yellow blocks, which half its previous until the height expands into two sortable elements. That's called a disperse. Okay. Blocks are periodic with their column. So total number of sortable elements must be a power of 2. So that's we need the null one, right? So you make those basically all bits on high number or something. So you go h equal to times 2. Right. So you do a swap basically. And then on the first one, then the rest of them disperse. I'm not sure what that does. Yeah, I'm confused reading this thing. Let's read it one more time. Ah, Gen Z video, just up my alley. Ah, Gen Z material, thank you, appreciate it. Right, let's jump this up. It's 26 when it was on here. Yes, this is where it's been solved recursively before in that other example. Alright, I see. Oh, that's magic. Pure magic. I don't know how you expect to understand it by reading the blog, but okay. Oh my days. Uh, we. Oh. Yeah, that is a much better explanation. Thank you for, for that. That was good. That was good. Music too loud. I'm sorry. I got you. Blast that music. Alright. Okay, so now that we know that we don't understand it, we can just copy and paste it, right? Is that what you're saying? Is that what you're saying? Um, but yeah, so the way this is saying it is it's going through these steps basically. Um, right. Um, okay. So effectively, we can just. Right. So should we organize our data first? Alright, here's how we're going to do it. Right, U32 sort keys. Alright. So we'll put the depth in the higher bits, and we only need 8 bits to reference 256 numbers, right? So 24 bits for depth, and the rest can be used for. So we can just do, here's the key, that's your sort key, right? So you'll say bits from F32, something like that, I forgot what it was. And we can say depth squared. Now, this is in sort of like a squared space. So the numbers are probably going to be they could be quite big actually. So it might be best just to square root it. Anyway. So then you've probably got to multiply your depth by something that's like, well, you turn it into an integer, right? So what sort of precision do you want? I don't know, right? So just times it by a magic number 1,000. So then you probably want to shift left that by 8, right? Put it in the higher bits, so it's more important. So therefore, when you sort it, it will make the number bigger, or smaller, right? And then we'll store the sphere index in the low bits. So we'll just say sphere index. So that's the information we're sorting, right? And then we can extract. We can go over all these sort keys and just extract the sphere index out, and then we're done, right? So, and the hope is this is all loaded into cache because we do this here, right? So we load into cache. So hopefully, a sort of randomized index or indexing into the array in a sort of random fashion, and when it's all sorted, shouldn't be that bad. So there's your sort keys. Now we need to do the sorting algorithm. So, I guess there is a barrier. Yeah, you need a barrier. The reason why you need the barrier is because you could have, yeah. Yeah, because not all the threads be in lockstep, that's why. Oh, stepping in waves though. We shouldn't be stepping in waves. Cell size is 8 by 8. Um, okay, so I guess we'll just do one of these. And we'll just drop them up here. You know, super organized code. We'll just give them a little bit of a rework. So this would just be S32. I don't know, why do we do this? Why do we not just have index A, index B, right? Some of that ought to be good enough. It's in a local value. We'll just do the sort keys, right? G's for so there's this thing called dflip. You put in pass in like a thread index, and this thing called h. For some reason, whatever h means. So thread index. H means half, doesn't it? Probably half index. I'd imagine that is what it is. Because you're doing can't quite pinpoint what it is, so I'm just gonna call it H. Right. So your indices then. So is A, B, A, in brackets just there like that. Voila. Let's do that anyway. Okay. So IDX A, IDX B. Very good. So there's that one sorted out. Just go select this one here. So pass in a thread index again, and this H thing, whatever that is. And then we'll do this. Look at these again. Just got to be careful, make sure that they're right. So this is T mod. This is the second one's slightly different. Yeah, slightly different. Cool. Then your indices go in there and do the swap. Rightio. So now we can just copy that for loop code here. So we need to pre-initialize them with a bunch of must have 2 elements in local memory, as there are twice as many Each worker must save 2 elements, as there's twice as many elements as there is workers. Right. Okay, something to keep an eye on. That's specific to this thing. So we just need to copy this for loop, and then just do the sorting here. So the barrier is, what is the barrier? It's a control barrier, I think. Yeah, control barrier. I'm not sure which one it is though. What barrier do I want to do? Lib, HCC, atomics? Wave intrinsics, atomics. Probably atomics. Yeah, so control barrier, dispatch group, this one. Waits for atomic mutations and for all threads within a group to be... Yeah, waits for all threads, all waves in a dispatch group for continuing. Perfect, that's what we want. So it's going to wait here. So you have multiple waves running in lockstep for this group. And you want them to wait there. Is that really good? I don't know. We can optimize it later. It's questionable. So we haven't filled up with null keys yet. So realistically, if you go over, right, you should be going up to threads count, which would be a power of 2. No. Sorry, you're going to be going up to this thing here, which should be a power of 2. And everything else needs to fill in a null key. So what you're saying is you should place in a 0x. Like, what do we want? Like, we want things closest, isn't it? Yeah, so we'll put all bits on. Perfect. So if we look at that, yeah, it should be fine then. So these ones will get ignored and be put at the end of the list. I think that the sorting says if it's less than. I think it's like if it's less than. I'm not sure how this sorting thing works, to be honest. Naive comparison, compare is smaller. Wait, where is this done at the bottom? Oh, interesting. Updated shader code. Oh no, why didn't I look at this one? So that's the comparison operation. Want to compare instead of... Oh, H stands for height. What is all of this stuff? with larger numbers of sortable elements. Right, so I guess it's on like bigger data or something, which I'm not too concerned about. Okay, so that seems like it's going to sort in the right order. So how much of this compiles? We're missing T, thread index. Then we need to pass in thread index. So thread index here is this one, isn't it? The right one, isn't it? Local index in a group. Yes, that's the right one. Excellent. So, N, how many times are we doing this? Up to spheres count, capacity, which is power of 2. Okay. So we haven't actually plugged it all in yet. We just got to finish up one last thing. When we go over here, we need to go over the sort keys instead, right? So you're going over the sort key index. So sphere index equal G sphere sort keys, sort key index, and 0xFF, right? We just want the first 8 bits. And that would be the actual one that we want. So this one needs to go over the sort key index, and we're going over how many we have spheres, right? And that should be it. Bear in mind, we could probably crash the GPU here. So I'm just going to sync. Yeah, just got to be careful. Probably could crash that GPU. So let's see how this sorts and see how it goes. So the speed we're getting was about 4.6 ms. So we're definitely going to get something slower, but then we can early out potentially. So just got to see how this goes. So you ready? Right. No. We're still going, but my... Right, let me log out and log back in. Right. Let me log out and log back in. BRB. Oh. Right, we're back. Awesome. So, yeah. GPU crashes. What you gonna do? What you gonna do? So just see if we can track this thing down. So, sort key. Put in the swaps, right? A, B, B, B. A, B, 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 B. So we're just gonna double check the code. Make sure we're all good. This won't scale above Vulkan limitation. It will, alas, not scale as hardware limits apply. There are two major hardware limits. One is the volume of... Yeah, I think this is fine for us. Our dataset's quite small. And And are we actually a power of 2? Yeah, we are. We are a power of 2. Right. Quickly check. X, X, Y. Y, X, Y. X, X, Y. Y, X, Y. Perfect. Just does the swap. Good. So we did this sort of 2 times thread index divided by h times h. Q plus thread mod that. Yep. H take T mod that. Yep. Okay, the disperse one is the same for the Q. Yep. The same for this one. But is plus off. Yep. So these are good. So let's take a look at my code now. So we added this and this, and we changed this. So 256, it won't go over 8 bits. Right. So we could not sort them. So if we didn't sort them and just put them in there, and we run, like, we can disable this code, and if it still crashes, then it's something to do with this. That's one test. Base sphere index, yep. Let's go all the spheres. If it's less than the count of spheres, we get the sphere, do the check, cram it in there. If not, we put all the bits on. You've got enough to store this many in there, it's about 256. So that's looking okay to me, I'm quite happy with that. This one though, maybe need another barrier. After, I'm not sure. Right, so what we're going to do is we're going to put a barrier here. I'm going to comment out this. If it crashes, then we got a then it's this code. Or potentially the code below. So we've stuck in the low bits. Oh, base index. There's your problem. Right, I found the issue. I think. Base index is... Oh no, it's not. It's still the same. Because this is the one is this big array. H divided by 2. Yeah, that's what the code said it had to do, is the H divided by 2. No idea why. Do you keep resetting? Does it keep setting H again? Yeah, how does that work? Seems like it shouldn't go any more then, should it? Huh. Yeah, how's that expected to work? Yeah, see, I don't fully understand this sort of logic. We saw how it worked in a video, but it seems, and yeah, they've designed this for loop to do it. In H, local disperse. This is some other code. Yeah, but that for loop doesn't seem to make any sense, does it? Because you're doing like a divide by 2, but you start off at 2, so you must be able to set H again. But I'm not seeing any H being set. H doesn't get modified. That's confusing, isn't it? Right, this... Yeah. Yeah, here it says times equal 2, doesn't it? But then it's like it's got even more complexity to it now. There's like a global and a local. And maybe we just copied it halfway through the explanation. So from a binary merge sort for local elements up to the maximum number for H. Was a progressively diminishing disperse operations. Was a full flip. I didn't realize there was different versions, not gonna lie. Hmm. Might see there's a more simple example somewhere. Yeah. Yeah, there's some issue. I'm not sure if it's this. Yeah, just ask ChatGPT, man. Get the sort key. Um, plus thread index. Threads count. Oh, this might go over the edge. This, well, maybe not. Power 2. Should still do the check. Fill it up. Right, let's give this one a go. If the stream crashes, I'll see you in the next one. I might as well just bail because it's kind of getting to the end. But if it doesn't, we can all celebrate. It doesn't crash, and it's something to do with this, if so. But yeah, so I guess I'll just say in the next stream, we'll be trying to optimize, just, trying to do more optimizations on this ray tracing stuff. Like just optimize the shaders basically and see sort of how many spheres that we can work with if we were to ray trace them. But yeah, right, so let's give us a go. Right. Oh, it goes. It works. Right. So that is populating it using the sort key. So the code that's crashing is this. Right. So yeah, we need to find like a good Bitonic sort. Okay, I thought, how is it this simple? Well, it ain't. Particle buffer. Where's the sorting, man? Oh yeah, get out of there. Right. But yeah, I think we've got to find a good implementation of Bitonic sort basically. If you want something simple, you need to stay away from shaded toy. Yeah, maybe. I know there's some simple examples on shaded toy. You just got to find it. There's some good stuff. Right, this one looks right. A naive Binary algorithm GPU based on the blog was just looking at. Great. Based on the blog was just looking at. And then written in WGSL, whatever this garbage is. At least they've got numbers. What is this language? Oh, it's JavaScript, right. But there's... Oh, right, okay. GPU JavaScript, yeah. So we can't really compile on the CPU, but yeah, we could, well, I guess we could, yeah, copy paste it. But we're kind of relying on each thread getting its own index, but I guess, yeah, that's another way of doing it. Yeah, it's still possible probably to debug it CPU side. We can also print from GPU and make it not do much. I can't see any. Right, here it is. To do that disperse and stuff. This is part of the problem with like this algorithm being kind of magical. Is you have to invest time in properly understanding it. Algorithm local flip or local disperse based on what you've passed in, I guess. So where's the... I still don't understand it. Oh, it's the prepare. Where's the for loop? Dude. Oh well. Right. So off stream I'm gonna search for like a good Bitonic sort that we can sort of like look at. And then we'll or maybe just some other sorting algorithm or something, just so we can see how much it improves our performance on this shader. So in the next stream we'll continue optimizing this ray tracing shader, just so we can get some rough numbers, and then we'll obviously continue with this tile binning shader, maybe optimize that, and just sort of see how many spheres we can push at the GPU and how good we can make it basically. That's what we're doing. On Tuesday, 6:30 p.m. GMT plus 0. Because the clocks have gone back now. So we're back onto standard GMT time. So right, thank you for coming everybody. I'll see you in a future one. Yeah, have a good night guys. We'll just find someone to raid. Yeah, one of these. Yeah. Awesome, thank you. Right, let's figure out how to get onto the right thing because apparently we can't just get so much effort. Even if this is any channel I go on. If anyone has any suggestions, that'll be up there. Primarily C-based development, basically. But I can do others as well. Hey, it's Tad. I work with Tad. Let's raid Tad. I didn't realize he streams. Right. Have a good one, guys. See you in a future one. Have a good start to your work week in a bit. Bye-bye.